Welcome back to Automatic Control Systems. I am Professor Kalyana Veluvolu with the School of Electronics Engineering. In the last class, we discussed of modeling of physical systems. We focused mainly on electrical systems and mechanical systems. This class, we are going to focus on electromechanical systems. We already discussed about the working principle of a motor and the basic electromagnetic effects or how electrical energy converts into mechanical motion. In this class, we are going to specifically focus on modeling a speaker. Speakers are quite popular and we use speakers for various applications. So, this is the week 3 part 3. So, coming back to here, what is a speaker? Everyone uses speaker, iPhones, we use for listening music, we use for listening sounds. What is a speaker? Is speaker an electrical device or a mechanical device? Speaker is an electromechanical device. The input to speaker is an electrical signal. Based on the electrical signal, the speaker functions and produces sound. The sound we can hear. So, what is sound? Sound is mechanical vibrations. So, most of you, I am not sure whether you have seen a speaker moving. Speakers are very powerful. If you stand beside a big speaker, it can even blow you off. If you go to a big speaker and stand in front of, you can actually feel the vibrations. The speaker takes the electrical signal and produces mechanical vibrations. It produces waves into the air. These waves travel to the air and actually your eardrum can actually recognize these mechanical waves and convert into electrical signals which your brain can identify as sound. So, the speaker produces sound is in terms of waves. So, if you look at the speaker figure that is shown here, it is a cross sectional view. So, that means if you cut the speaker into half, you can see that. So, what is inside the speaker is the below part we have a big magnet. This is a big magnet and then you have an electrical coil and then it is a diaphragm and this is the outer one which you normally see on when you see a speaker. So, what happens is this is a permanent magnet, most likely a permanent magnet, and in the center you have a electric coil. So, actually when you send an electrical current to this coil, depending on the current, this actually it moves, this diaphragm starts vibrating. Depending on the signal, the diaphragm vibrates. The diaphragm motion produces mechanical vibrations into the air. These vibrations travel to the air and you can listen. Now, if you actually look here, this diaphragm is a mechanical motion. Then if you see, the input is an electrical signal to the coil. When you place a conductor in a magnetic field, it produces motion, mechanical motion. So, that is the working principle. So, this speaker, what we have given the next diagram is a cross sectional view, and what is a simple functional diagram. I can see the magnet and this is the cone, that is the air, and then the expanded portion of the magnet is given here. So, what you see here, this is the coil that moves in this one. This produces the mechanical motion. Now, what we can infer from here is when we send an electrical signal to the speaker, the coil produces the field, because of that the experiences force and it causes the vibration. Let us try to understand this one and then we start the modeling. Now, modeling a loudspeaker. So, before we talk, what is the load on the speaker? What is the job of the speaker? The speaker diaphragm tries to push the air, pushes the air molecules. We have a lot of molecules in the air, so it pushes the air. When it pushes the air, depending on the air volume and the air density. When it pushes, it transfers the wave force. So, this air forms like an opposition force, that is what we call load, just remember. Now, coming to this coil, this is several wire, the wire is actually rotated into several coils. The bobbin which has n turns of radius r meters. So, if you see, the force depends on the length of the conductor. If the length of the conductor, if you make several rounds, the length can be very long, and the force depends on the length of the conductor. That is why several motors have a lot of windings, coils. So, the length of the conductor is very large. When the length of the conductor is large, you can actually get bigger force. So, here our length of the conductor is 2 pi r into n, the number of turns into the radius of the each radius of the bobbin. So, you get the length is 2 n pi r. The mechanical equation follows from the Newton's law, assuming spring constant is negligible, is given by this one. So, what is this one? This is the opposition force. For example, the speaker is trying to push the air molecules, right, the air molecules. So, this air can be modeled in terms of a mass m and a viscous friction coefficient V. The effect of the air can be modeled as if the cone has equivalent mass m and viscous friction coefficient. Now, this can be confusing. How do we model the air? You see, a lot of these studies we already have the values for the mass or based on the density of the air and the friction coefficient. So, these values are generally supplied. You do not need to remember. These types of equations are generally given in the examinations. I will give you all the description. So, the students need to understand the description and try to model. So, you do not need to worry about remembering any of these terms. So, this is the equation when you have a damping, when you have viscous friction, the air effect can be modeled as mx double dot plus bx dot is equal to f. Now, just keep it aside. What is the force acting on the conductor is F is equal to B phi Li, which we learned in the earlier slides. Phi is the field strength, L is the length of the conductor, and I is the current. Now, we are going to use these two equations and try to develop the displacement, develop the transfer function for this. Now, going back to the slide here, what is the input, what is the output? If you look at the speaker, the input is the electrical current and the output is the mechanical motion of the diaphragm. The diaphragm produces a displacement x depending on the input current. So, we are trying to model the air molecules that are displaced, that is the diaphragm movement from the input current. So, I is the current, I produces mechanical motion, I produces force, force produces motion. Now, the force produced by the coil is B phi Li. So, here this I produces this force and this force produces the displacement. In the S domain, we can try to model them. When I try to model this equation with the Laplace transform, I get S square m plus SB, S square m plus SB into x of s equal to f of s. So, here if you try to understand, input in this equation is the force and the displacement x is the output. So, I write the output input relationship x of s equal to 1 by s square m plus SB into f of s. Now, choosing the second equation, let us choose the second equation, F is equal to B phi Li. What is input, what is output? Current produces force, current is the input, force is the output. In every modeling equation, you need to understand what is the cause, what is the effect, what is the input, what is the output. Then you can actually do the modeling. It is very important that you understand how the actual system works. If you understand how the system works, then you will be able to do the modeling very well. So, here in this equation, if you look, I is the input that produces force. So, I is the cause, F is the effect, or the current I is the input, F is the output. So, doing that, I have f of s equal to B phi L I of s. Now, if I write in the equation in the form we can write this one also in the form of a block diagram. Now, first take this function x of is equal to 1 by s square m plus s b into f of s. I can put it down into block diagram. What we see here, the force produces displacement. The force is the input, F is displacement. So, I can write as in the form of f of s equal to f of s 1 by s square m plus s b x of s. I would like to repeat that this model, this is the model that is defines the friction effects on the viscous damping of the air. So, sorry, here the friction is absent, it describes the modeling of the air. So, this displacement is depending on the dynamics. So, this type of models are generally provided. Now, coming back to here, we know the current produces the force. I of s can be written in the block diagram form of B phi L f of s. Now, we can interconnect these two systems. If you actually look carefully, the current produces the motion force and the force produces the displacement. So, we are going to connect these two blocks. So, current produces force, force produces displacement, then I can actually connect the two blocks. If we connect the two blocks, we have I of s, B phi L is inside, the current produces force, the first stage, and the force produces the displacement. So, now combining these two, I can write one transfer function directly from output displacement to input current. So, I can actually combine these two blocks into one block diagram. So, I can write as x of s by I of s is equal to B phi L by s into s m plus b. So, the beauty of block diagrams is we can interconnect many blocks and make it into one single expression. So, the block diagrams gives us the flexibility to even break into several parts or combine into one part, like we learned in the block diagram algebra. We learned about solving big block diagram into one simple block, or we can break a big block, small block into several individual blocks. So, finally, what we are able to do is we are able to model a loudspeaker from the input current to the mechanical displacement. The mechanical displacement is the bobbin movement or the diaphragm movement, and this diaphragm movement causes the air molecule to displace and it produces waves in the atmosphere. So, the next part we are going to go through another circuit. This is also a nice electromechanical application. This here we connect the speaker to a circuit. When we connect speaker to a circuit, its behavior is slightly different. We are going to understand from the circuit behavior to the output displacement. So, what we are trying to look here is we have this nice electrical circuit, the input voltage VA, resistance R, inductor current I, inductance L, and we have E coil, I am going to explain, and then they are connected to the speaker. So, when the speaker is connected to the circuit, this circuit drives the speaker. So, when this circuit drives the speaker, that means when you change the voltage, it changes the current changes the inductor effect, and because of that the displacement of the speaker changes with the change in the voltage. So, our objective is to formulate the model for the input voltage VA to output mechanical displacement X. So, I am trying to go through this model, output to input VA, output X. Before that, I would like to discuss one important aspect. The second most electromechanical relationship is the effect of mechanical motion on electrical voltage. So, when you actually place a conductor in a moving magnetic field of strength B phi at a velocity v meters per second at mutual rate angle, an electrical voltage is established across the conductor. So, that means what is trying to say is, if you place a conductor and move in the magnetic field, there is a voltage developed across the conductor. This is what we call law of generators. If I pass current through the conductor, it produces force. In the same way, if I in the magnets, if I place the conductor and move it, it produces voltage. This is law of generators. Based on that, what happens is when the speaker is moving, because of the magnetic field, because of the motion, it produces back EMF. Back EMF is something because of the magnetic coil here for the inductor, it produces opposite voltage. So, this is what we call E-coil. This will be more detailed. I think students will understand it in more from the electromagnetics. So, we have this back EMF coil here. So, this back EMF coil is placed to counter for the to actually this coil is the resultant, this voltage actually will represent because of the motion of the speaker. Now, taking this one, we are trying to develop the basic equation. First, we refer to the previous equations. In the earlier analysis, we have already developed the equations for the speaker, that is mx dot bx dot is equal to f and f is equal to p phi li. From now, we are actually going to develop only two equations. So, if you see, we have an electrical circuit here, we are going to write the equation of the circuit. VA is equal to IR plus L di by dt minus E coil. So, this E coil acts like a feedback. When the energy is supplied to the speaker, depending on the motion, there is a back voltage developed into the circuit. This E coil actually is like a feedback to the circuit. So, the E coil is based on our expression here, E is equal to B phi LV, based on the velocity of the motion. The velocity is the motion, the velocity of the diaphragm. The E coil is B phi L into V. V is x dot, x is displacement, so velocity is x dot. So, B phi L x dot. Now, if you look at the electrical circuit, we can actually model the electrical circuit into a simple form, L di by dt plus R is equal to VA minus E coil. Now, if you look at all these equations, first once you formulate all this equation, I want the student to understand what is input, what is output in every equation. Now, let us start with this equation. Force produces displacement, F is the input, X is the output. In the second equation, current I produces F, I is the input, F is the output. And here, because of the motion x dot, we get the E coil. So, x dot is the input, E coil is the output. And now, coming to the electrical circuit, VA is the input, current is the output, right. So, if you look here, we apply the input VA, we get the current produces force, force produces displacement. So, this is where we try to understand. So, now for clarity, go back to the speaker. Voltage produces current, current produces mechanical force, force produces displacement, and then because of the displacement, E coil voltage comes. So, this is the understanding you should have. If you understand this way, the modeling becomes easier. Do not try to only learn the mathematical. If you just write the mathematical equations, many students fail to understand what is the cause, what is the effect. So, if you actually know what is the cause, what is the effect, it becomes easier. Always look at the whole picture, try to understand the working principle, try to relate every quantity as input output, and then the modeling becomes simpler. Now, let us try to analyze one by one. So, applying Laplace transform to these four equations, we can get the Laplace transform. We can get the Laplace transform. So, the earlier one we already formulate x of s is equal to 1 by s square m plus s b into f of s, and f of s equal to b phi L I f s is a small mistake. So, and now the E coil is actually obtained in the form of E coil is S b phi L x of s. So, this is the E coil. Here x of s forms the input, E coil E C of s forms the output. Now, the last equation we have is because of the feedback. We have this type L di by dt plus Ri is equal to Va minus E coil. Now I can actually, when you apply Laplace transform, it becomes SL plus R into I of s equal to Va of s minus Ec of s. So, or I can write I of s is equal to Va minus Ec by SL plus R. Here we can't separate Va Ec, which we will go through in the next. Now we can form the individual blocks. Taking these 4 equations, for each equation we can formulate an input-output relationship. The first one, x of is equal to 1 by s square m plus sb f of s. We know that force produces displacement. Write the relationship by f x of s, f of s 1 by s square m plus sb. Now take the second equation, f of is equal to b phi L I of s. So in the second equation, I of s is the input, f of s is the output, b phi L. Now the third equation, Ec of s is equal to s b phi L x of s. So when we write in the form, this is important, x of s is the actual output of the system, but however in the E coil it acts as the input. So when output acts as the input, it is the feedback. Very important, when output becomes an input, that is a feedback. So x of s goes to this block and we get the output is Ec of s, that's we understand as a feedback block. Now the current I is equal to Va minus Ec of s by SL plus R. So how do we write in the block diagram is Va minus Ec. So you have to write as using a comparator, we write Va of s is the input, Ec is minus, Ec is the coming here as minus, so that goes into the comparator. The output is 1 by SL plus R, the output will be I of s. So this is where we can actually formulate. Now the most important aspect is, the important aspect if you look here is identifying the input and the output. So the primary input here is Va and the output here is x of s. So we are trying to connect these two, and when you are trying to draw the block diagram and you have all the individual parts, this is a very difficult part. Many students find it difficult to complete the block diagram. I have seen many students complete all the block diagrams, individual equations, but then they cannot complete the block diagram. This is because of one reason, they do not really understand what is the input, what is the output and what forms the block diagram. Should always be started backwards. First identify the input, identify the output and work backwards. When first start at the output, what produces x of s? If you try to go back, if you try to go through this equation, what produces x of s? What produces x of s? If you go through, the force produces x of s. Draw this equation. So what we are trying to do is start at the output, place the input, place the output, start backwards. So first identify this block, f of s equal to f of s x of s. So 1 by s square m plus sb. So the force produces x of s. Now what produces force? Current produces force. So this is the second block, the current produces force, force produces x of s. Now if you come here, where do you get the current? Current comes from Va, the input, to the I of s, and now you have Ec of s. So based on that, if you look, the only thing that connects the output to the input is the feedback. So start at the output, you get x of s, f of s, then you see that I of s, f of s are related b phi. Here I of s is the input, f of s is the output. And now in this equation, Va of s is the input, I of s is the output. Now when we make the full connection, we have this feedback that is connects from the input to the output. Any equation, when the output becomes the input, it is the feedback. There is no block after the output and there is no block before the input. Very important. Everything is between E VA of s and x of s. So, once you formulate, we have this block diagram, and then we can actually combine into one nice block diagram. This way we actually combine all the block diagram, all the individual equation into one nice block diagram. So, the interconnected equation gives in this form. When you have this block diagram, always compare with this one. When you compare, you can see the individual block and the circuit, and you can see the input VA, output X, and the relationship, everything is here. So, a physical system is modeled in the form of input output representation, we call block diagram. Now, we can actually simplify, solve this closed loop system into a block diagram, into a transfer function. I can write x of s by VA of s equal to B phi L by S ms blah blah into this kind of nice transfer function. The next, we are going to actually learn about rotational systems. Until now, we learned about electromechanical systems. From now, we are going to actually go through rotational systems. So, rotational systems are the systems which actually rotate, that involve a fixed axis rotation, like wheels, car wheels, they are fixed, so they rotate about an axis. So, they have very many important applications. Everything that moves in the real world needs rotational movement. So, let us have a look at a simple representation here. Consider the mechanical system, consider the rotation mechanical system shown below. It can model like a electrical vehicle, in any vehicle, wheel of a vehicle. So, what we have here is the wheel that is connected to a fixed plane, and this actually moves. So, there is quite analogy between mechanical and rotational systems. So, there are few things here. I think if students really follow well, it can be very easy. Now, what are the quantities here? What we need to understand is, in mechanical systems we have force, mass, B, P and K no much change, X, X dot, X double dot. So, these are the quantities in mechanical systems. In coming to rotational systems, F becomes torque, mass becomes moment of inertia, B is written as rotational viscous friction, rotational spring constant, and now displacement is in translational movement, is in linear movement, rotation is angular. So, x becomes theta, x dot becomes theta dot, x double dot becomes theta double dot. This is what we called acceleration velocity, we got omega, this we called acceleration, we got alpha. So, these representations will help you understand much better, because if you actually look at some of the relationship, F is equal to ma, right, torque is equal to I alpha or I theta double dot. So, this way we can have every one-to-one relationship. There is clear relationship between every relation in mechanical translational systems to rotational system. So, when you learn, please connect with the translational systems which you know, and then it becomes much easier. So, coming to here, I will just try to explain in a very simple way. So, we have motion here. So, if you actually try to break this one into a free body diagram, what actually here is, this k theta is because of the spring, rotational spring, B theta by dt is viscous friction because of that, and T is the torque, rotational torque. Rotational force is what we call rotational torque. J is not mass, J is moment of inertia, it is also represented by I or J. So, you can actually represent with I or J. So, the torque equation, if you actually try to convert this one, you can actually develop into a very simple equation, J dt square by dt square plus B dt by dt plus Kx equal to T. How do you get this equation? Is, if you see here, when you try to rotate in this direction, there are opposite force in the opposite direction. I am trying to rotate the wheel in this direction, because of the spring constant and because of the viscous damping I have opposite forces. So, when I am trying to rotate in clockwise, I have forces in the anti-clockwise direction. The whatever, just like F is equal to ma, rotational torque, the resultant rotational torque produces angular acceleration alpha. So, how do we, from this expression, what is the resultant is very simple. I can actually, from here I can actually write the expression for you as the torque minus B d theta by dt minus k theta produces j into theta double dot. So, this expression, if you can rearrange, you get this expression. This is the resultant torque, torque applied minus the opposition torque, you produces j into theta double dot. So, that is how you have j d square by theta plus d theta by dt plus k theta is equal to t. This is the way if you compare with the translational system, analysis becomes much simpler. So, you have the expression theta of s by t of s equal to 1 by j square plus bs plus k. You can transform this torque equation into simple transfer function, and this transfer function gives a relation between output angular displacement theta of s to input torque. So, you can formulate is 1 by j square plus bs plus k. Now, the main, if you look here, we have three main components here, the three main components of inertia, torsional spring and viscous friction. So, if you try to understand moment of inertia, that is like F is equal to ma. So, if you try to compare, this is equal to this is like F is equal to ma. So, this is like F is equal to ma, and this is like torsional spring F is equal to kx. So, it is very simple, you can write if this is also is equal to F is equal to kx. So, you can actually relate the translational equations to rotational equation. So, if you try to see here, torque is equal to j into angular acceleration, F is equal to m into a, or if you apply a torque, it produces angular displacement. So, this is related to omega, theta dot is equal to omega and omega dot is equal to alpha angular acceleration. So, I can write torque is equal to j d omega dt. Next, coming to torsional spring, torque is equal to k into angular displacement. So, I can have torque is equal to k into theta 1 minus theta 2 in this expression. So, if you see here torque, the spring is, any material has spring constant. If I are looking at this kind of thing, if I try to rotate, apply more force, this also bends. This is what we call spring constant of this material. So, some material has very small spring constant, some material has very large spring constant. So, every wire, every material has different constants based on its mechanical properties. So, there are spring constants for many systems. Next, viscous friction. So, if you are looking at viscous friction, it is similar to our earlier expression, torque is given in the form of B is equal to B theta or F is equal to K into dx by dt, sorry, B into dx by dt, that is what we learned earlier. So, it is directly related to this expression. So, in this way we can actually identify or compare with the translational systems, compare with the rotational systems. So, all these three form the basis of description for rotational systems. In the next class, we will actually go through with continue with the modeling of electromechanical systems. So, what we learned today is about modeling of rotational systems. We also learned about basic components of the rotational systems. Next class, we will actually go in depth modeling and we will be going through nice applications. So, that is all for today's class. Thank you. End of week 3 part 3. Kamsahamnida.